Hi guys. In this lesson, we will discuss the ways to give thickness to the surfaces in Alias, as well as common issues comes with it, and overall pipeline in the industry for thickness and how Alias contributes to this pipeline. So, when it comes to thickness, different CAD systems treat it differently. Solid body and generalized systems treats thickening process as a solid body object construction. Solid body is an object that has material inside the thicken element. And by material, I mean specific parameters as type, density, plasticity, weight, and other physical properties. And surface modeling tools like Alias doesn't understand that concept of solids. Because of that, different systems use different tools to create thickness. Systems like SolidWorks, Fusion 360, Rhino use tools like thicken or shell, while real A-class surfacing tools like Alias use offset commands. Offset commands in general exist in all the CAD systems, as well as vector and raster editors, so it is universal. And this universal tool, or better say its basic algorithm, is at the core of all thickening commands. So if you strip away all the bells and whistles, which are extremely useful, let's say from shell command in Rhino, you will end up looking at basic offset functions at its core. That said, offset command is a basis for all thickening commands, and in Alias specifically, offset command is the only way to give thickness properly. But don't be fooled by that simplicity, as offset command in Alias in general is much more robust and give you much more control than in solid body modeling counterparts. It can give you solids in return, yes, but it can give you much more direct control than shell or thicken commands in solid body modeling tools. Sadly, even that is rarely enough, but before tackling it, let us look at offset commands Alias provides us, figure out how it works, and through that, understand why giving thickness is such a painful process in CAD in general and in Alias specifically. So we're in Alias, so let me start by just a simple curve. So let me zoom in, and this is our curve. As you can see, there is not one but two curves. They are continuity. They have a continuity constraint. So this curve aligned continuously to this one. And imagine that I would like to give it thickness to basically offset one of the or both of these curves in the normal direction. And in general, when we're talking about the offset or giving thickness to something, we are talking about the normal direction. So it's supposed to be shrink or expanded based on the normal direction. It's not always the case. We have options in Alias and the other tools to change the direction, but in general, when we're talking about the thickness, we're talking about the offset along the normals. And when we're talking about the offset tool, we imagine that we are moving something along the normals. So let me go in and activate the tool. Now, once again, we're starting with the curves. I will get to the surfaces eventually, so don't worry. So the control, or basically the tool itself, so the curve offset and the surface offset are very similar in terms of controls. The surface offset tool is much more robust, of course, than the curve offset tool because of the two-dimensional domains of the surfaces, but we will get to that. So the curves, the basic controls here are right in the top, so under the offset mode and distance. And here you're going to see 4 radio buttons. They called automatic, CV offset, explicit, and original. Now, they are extremely important because they actually are different algorithms for the offset command. Now, there are 4 of them, but actually there is only 2 very distinct, like completely different algorithms. One of them called automatic and another one called CV offset. The explicit and original are as subsets of automatic, and the CV offset stands by its own. So let's start with automatic. So what I'm going to do is I will just click on the curves. Let me change the direction inwards. I will talk about why we need to do it inwards, not outwards all the time. But for now, let's say that I have an offset here. And if you look at the curve, you immediately notice that the newly created curve is quite different than the original one. First of all, we have quite a few spans here, like literally a lot of spans. And actually, if I will select one of the curves, you're going to see it has 11 spans. And this one has 9 spans. Well, we have a single span of simple curves, just, 3 degrees for control vertices. And here we have, for example, 3 degree 11 spans. Oh, why was that? Now, in this algorithm, the complexity of the curve defined by a tool, by Alias itself. And the main premise of an offset in general, no matter what kind of algorithm you pick, is to maintain equidistant. So the distances between the points on the curve and points on the original curve and the points on the offset curve supposed to be equal. So that is the main premise of the offset command, of shelling commands, of thickening commands. It depends on the tool. They maintain this distance because this distance is actually extremely important property when you create thickness to the model, because on the mass production, when you do like pressure casting, for example, you need a matrix and die. And for them, this gap, this distance are extremely important because you will be pouring material inside of it. And if there will be too big of a differences, then it can lead to, to discrepancies in the final product. It can bend or break or whatever. There is a lot of issues with that. So this behavior of an offset command and all the other related to the offset tool in other generalized software packages is kind of the main idea for that. And as a result, the concept of making good quality curves, well, in our case, it is curves. In the surfaces, we will talk about the surfaces as well. And the continuity between them is secondary. This is not the main goal of this. And even if it was one of the main goals and two of them are equally important, Alias will not be able to do that. And not only Alias, but any other system as well. This is the fundamental flaw. But to really understand it, we need to dig into it a little bit more. So for now, if I will just use the curvature comp here, on the original surface, you're going to see that this is very, very natural and very accurate. So we have a positive acceleration, inflection point, and then the negative acceleration. All smooth, all accurate, no issues. But the moment when we check this one, let me just expand it a little bit, you're going to see what is happening. So as this curve has so many spans, it brings irregularity to the curve. And even though the distances are very, very close to each other, so in this regard, the tool did its job, the surface itself and its curvature is actually quite distorted. So you're going to see this wobbling, right? So here and then here. But this is not the only issue, of course, because if I will zoom in, let me just zoom in and zoom in. Okay, here it is. Now you're going to see that we actually have not only the issue with the acceleration along the curve, but the connection as well. So we actually lost curvature here. So in other ways, we have a curvature deviation. So this is not a curvature connection anymore. And if I will zoom even closer, I will see that it actually failing on tangency. Now the angle is very, very small. It may be within our tolerance set or my tolerance set, and it will not be an issue, but the curvature definitely will. So these two curves are not connected, not only as a curvature, but we actually failed tangency as well. So, well, you may say, well, this is very undesirable. I don't want this result. So what's going on? Now, first of all, let me quickly dive into the second algorithm, and then I will describe both of them and why they give you this poor result. So let me go to the history and change it to the next method. So instead of automatic, there is another one called an offset. So if I'll click on the offset, and once again, I will explain in detail what actually happening here. You're going to see that now our curves are very accurate and smooth. They're actually the same parameterization as the original one, but they're lacking the continuity even more. So you're going to see there is a huge gap in curvature now, and really little in a tangency. So once again, we're failing both curvature and tangency, but at least here we have, a good curve. But if you look closer now with this method, it's actually visible by an eye that the distances are not equal. So even though that we have curves, the accurate curves here, we are failing continuity, and now our distances are wobbling, and quite significantly, actually. So to really understand what's going on and why we have this issue, we need to dissect or deep down into the algorithm of automatic NCV offset and understand why it's giving us these results. And for that, I'm switching to the different tool. It's called Grasshopper. It is a parametric modeling plugin for a Rhino, where let me actually open it up. So I actually quickly reconstructed very basically, of course. It's just a very blend depiction of what Alias instruments actually have. Alias instruments are tenfold more complex and more accurate than what I have here, obviously, but it just shows you the general approach. So what you're going to see here is the same curve brought here from Alias. And as you're going to see, I have the curvature comp plotted already, and you're going to see it's the same. So this is the same curve. Now, when we're talking about the automatic algorithm in Alias, what it means is that Alias will take a original curve. It's subdivided on multiple segments, basically populated with the points. Let me just activate the points like this. So now if you zoom in, you're going to see there is a lot of points on this curve. Quite a lot of them. Now, Alias will populate it differently, not like me. It populated non-uniformly, so where will be more curvature will be more points, where will be less curvature will be less points. Now, mine, as I said, very blend depiction. So, but the overall concept is still the same. So you populate the points, then you will find a normal direction of the vector at the normal angle or the 90-degree angle to this curve, and then Alias constructs the vectors. Now, the vector has amplitude. It's one of its main properties. So direction and an amplitude. And this amplitude is actually the same thing as in Alias here when you have the offset distance. This is actually the vector. Now, Alias will show you only one, but there is actually a lot of them. So, oops. Okay, so so we have all of these vectors. After that, Alias will construct points on the ends of these vectors. So it basically adds up the coordinates with a scalar value, and then it will get another correspondent pair of points. So for every point on the original curve, there will be a corresponding point on the normal direction with a specific distance, right? And after that, Alias will reconstruct the curve. Now, my script, of course, works very basically, so I'm defining how complex of the curve it will be. Alias does it itself with a lot of other constraints, but eventually you will get the line. So let me now hide the points and hide the vectors. So, and now we will have this curve. So this is basically the reconstructed curve based on the points which were offsetted from the original points on the original curve. And that's how Alias will reconstruct it. Now, to do that, you need quite a lot of the geometry. So now, as you're going to see here, for my rebuild curve, I have 4 degrees for every segment, and I have 14 control points. Now, the Grasshopper, in comparison to Alias, even though that it operates with the same math and concept of NURBS is literally the same, the way how we treat it and how it visualizes information is quite different. So you probably remember that in Alias, you can't go more than the power of 9 or the degree 9 for a single span curve, right? As well as surface. Well, Rhino can give you an option to go beyond, but not necessarily, because actually you define the amount of control points, but you're not specifying spans. So basically here, I don't see how many spans this curve have, but trust me, there is a pretty big number, and it's easier to calculate because the formula, once again, math is equal everywhere. It's very simple. So you can do it the same as you can do it in Alias. So you will take the amount of control points, subtract the amount of degree for a segment, and add 1. So it will be 14 minus 4 plus 1. It will be 11 spans. So this curve has 11 spans, and this curve has 11 spans. Well, now if I will activate my curvature comp, you're going to see that, well, we actually have a very similar result. So you're going to see that the curvature is breaking here. You see there is this, here very visible, the discrepancy in the curve. Here is discrepancy, here is discrepancy, here is discrepancy. And of course, if I will zoom in, where is it? Oh yeah, here it is. If I will zoom in, you're going to see that I have a curvature deviation and a tangency deviation. Same issue. Same issue. But we are striving for the equidistant, right? So this is in general the automatic approach. And this curve, to reconstruct it properly, is supposed to be much heavier than the original one. Now, why was that? Well, that's because when we shrunk something, when we make it smaller with a very specific constraint, which means normal direction, our parameterization of a curve changes. And it was fluid and natural in one state. When you shrunk it, it became to be almost impossible to maintain curvature and at the same time have the proper distance between them. Right? So the tighter your bands, the more aggressive your form, then harder it will be to shrunk it and keep your curvature. Because once again, all the parameterization changes, all the angles will change. And sometimes it can come to the situation when you have like overlaps, right? Because there's just not enough room. But even if it is enough room, like here, you're going to see that maintaining the proper distance and at the same time make it curvature as it was become to be a very challenging task, extremely challenging task, especially when we're talking about the complex surfaces. In curves, it's a little bit simpler, and Alias actually can get you covered with that, and we will talk about that in a bit. But this is the overall limitation and the problem with an offset in general. So we talked about the automatic approach, but I said there is two different distinct ones. The second one is an offset. So let me actually hide this and hide this. And now we go to the next method called CV offset in Alias. So the CV offset method works differently. It takes the control vertices of your curve, not the points on the curve, control vertices. So basically I'm talking about these points, right? So it takes these points, which you kind of move to change the parameterization of the curve, right? So it takes these points, here you see them right now active, and then it offsets them on the normal direction to the curve. I will not be discussing all of the shenanigans in the scripts. I probably will do a different series about the grasshopper because it's really useful for cut sculpture in for cut sculpting, for concept design, for a lot of other stuff in the industrial design in general. But that's a story for another day. So here you're gonna see this is the offset of these points in the normal direction relative to the curve. Right. So what Alias will do is it will create these offsets on these points, right? Here, 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 here. And then it will reconstruct with a new curve, a NURBS curve, with the same amount of degrees which original was. Of course, it can't do it any other way. So if that was a 3-degree curve, it means it has 4 control vertices. So 3-degree curve, 4 control vertices, 0, 1, 2, 3, 4, and 0, 1, 2, 3, 4. And then it gives you the curve. Now, the abilities of the grasshopper and rhino are not as robust as an Alias. So you see here, even it's easier to see that the distances are quite different. So this is definitely bigger. This is definitely smaller. In Alias, this is not that big of a difference, but still there. Here, it's very prominent. So yeah, we made an offset. Our curves are better, but we sacrificed our distances. And in fact, if I will activate the curvature comp, you're gonna see that, yeah, it's much more accurate now, but the gap is even bigger. So now this is a really significant break in curvature and pretty significant break in tangency. So yeah, we sacrificed the quality of the curve for the gap and continuity. So now it's just even more, it breaks even more. But this is a kind of a second option for you. As you can see, none of them are actually ideal. Every one of them forced you to sacrifice something, right? If we're talking about the automatic method, it sacrifices the quality of the curve or the surface, when we will talk about the surfaces. And when you're using a CV offset, it sacrifices the distance and the continuity for the quality of these segments. Okay, so now let's get back to Alias. Okay, so now when we figure out what both automatic and CV offset does, we need to go through the explicit and original before we move on. So Explicit and original, as I said in the beginning, is a subset of an automatic method. So it starts the same way. It populates the points, it moves the normals as I showed you in the grasshopper. But then there is an option in explicit. Instead of Alias takes the complexity of the curve on itself and calculate it based on its tolerance, based on the deviation tolerance and a lot of other stuff. Here, it gives you an ability to define what you want. How many of them do you want, right? And you may say, well, I want to have 3 degrees single span. Well, and Alias will use automatic approach, populate, move, reconstruct, not the CVs, but the actual points, and then give you this curve. Like, yeah, here, eat it. And if you look at this stuff, you're going to see that. Now I ask it to make it 3 degrees, and it did it. And it looks pretty fine. But if I will check the curvature, well, yeah, that's not enough. So when we're talking with the automatic approach, when it populates the points and it's designed to make it the distance as close as it possibly can, just this amount will not work. It's just too small. You're gonna see how big is the gap. It's just huge. But you know, this is an option for you. Now another option, and it sometimes can be quite useful because of course I can just define how many I want, and yeah, I'll probably do 3 degrees and then I'll increase amount of spans until I kind of find some decent result. But as you can see, I have 65 spans, right? That just makes no sense, right? Maybe let's say, well, this one looks good. How many? Okay, 9 spans, right? So instead of oops, sorry, I accidentally turned it off. Okay, let's go back. So instead of original 11 spans as it built me, I can build it in 9 spans, right? Nah, no, it still looks like shit. So Alias suggested 11, right? So I would say 17. Okay, 17 is better, definitely. But you get the point. So this is what explicit does. It's still a subset of an automatic. What's about the original? It's very simple. It is the same subset of automatic, but it always takes the original degree. So if that was 3 degrees, it always gives you 3 degrees. You can't change that. Simple as that. So as you can see, 4 options, 2 major ones and 2 additional ones for an automatic. Now, before we move to the surfaces and figure out the shenanigans with the surfaces, let's quickly look at the options. Most of them are, self-explanatory, but I would like to put your attention on let me go back to automatic, onto the 2 important components. One of them will be important later for the surfaces, and one of them is important right now here. So in the more options here, you're going to see that there is an additional parameter called deviation tolerance. Now, in Alias, there is quite a few tools which have their internal tolerance parameters, because these parameters are not defined in the construction options to your document. And the reason for that is they are working only within very specific operation, because here in the construction options, there is no information about how accurate the offset is supposed to happen. It says a very unique operation within the tool, and that's why its tolerance is within the deviation tolerance, right? So the max span length is a maximum distance, or sorry, mean span length is the minimum distance for the span, or the length of the span. If you don't want a million gazillion spans with extremely tiny lengths, which you don't want actually, then be reasonable with that. Now, my tolerances are very, very tight because I'm working with a lot of small objects and consumer electronics. But for the car, for example, it is just these parameters makes 0 sense. Okay, so the next important component here, and I believe the attach and cut curve loops, I believe it's self-explanatory. It cut the curve if it loops, and it attaches the curves if it touches each other, right? Touches the ends. So there is one important one though, which is a keep continuity. Now, if I will go in and I will keep continuity, and I will go for let me just actually zoom before I'll do it. So I will zoom in where our break was, and our break was here, right? So it's still here, we didn't change anything. So if I will click on keep continuity G2, whoa, look at that. Well, Alias is very smart. Somehow it manages to maintain the curvature. Why it's not doing it by default, you may ask? Well, because it is a bias. So it defines the distance first. And by keeping the continuity, it will bring a distortion into the distance. Sometimes it becomes to be a big no-no. Sometimes it doesn't matter. Sometimes the quality of the offset become to be more important, which is rarely the case, to be honest, but you have this option. But don't rely on that too much, because when it comes to the surfaces, this tool is useless. This option is useless. It will not give you, it either give you even worse result, or it will give you no results. So this is not a magic wand. It will not solve all your issues with the offset. It can help, and I'm really glad that Alias incorporated it into the relatively new curve offset command in comparison to the old one. So this is a big step up, but this is not a savior for you. It is here. Sometimes it works, sometimes it doesn't. Now let me show you the same with the CV offset. So there is the keep continuity command, and this is without continuity, and this is with continuity. So as you're going to see in the simple examples, it will work just fine. You don't have, of course, control over tension or anything like that, but you know, it kind of tries. So here we sacrifice the distance even more, but we maintain the curvature, okay? Sometimes it's become to be useful. Now, what else is important? Well, actually, everything else is self-explanatory. Now, both sides, I believe you understand, but it just does that on the both sides from the original curve. The blend maybe... yeah, let's talk about the blend, just very simply. So the blend is when you have, like, you know, the edge, like that, and you want to offset. Let's go to automatic again. And I would like to offset this. And if I will click on blend, you're going to see that it just creates a blend between the hard transition, right? So here we go. It's rarely used, to be honest, because you can't control it. You know, how much lead-in you want, what kind of acceleration you want. I mean, it's better to do it yourself. But what it does, it just extends, find the intersection, then create the blend, a transition. So will not rely on that too much, never use it myself, don't know that anyone used it. But if you ever wondered, is it like blend and keep continuity looks like the same? No, they're doing completely different stuff. Keep continuity keeps continuities, blend give you blend on the hard edges. Right, so and the offset plane is simple, it's basically the direction. By default, we always try for a normal direction, but there can be changes, okay. So let me turn this off, or delete. Let me undo this one. And now let's go to the surfaces, finally. So here, as you can see, I get quite a few examples. So let's start with now all the examples are basic, but even in these basic examples, you know, offset will give you a hard time. So let's start with the very primitive one. So this is a slot, or that's the geometric shape or form, sorry, called slot. So this is a cylinder. It is a periodic form. And the cap of the cylinder formed by an arc with constant radii, which means that this arc can build you a form, and this form is a hemisphere, so half of a sphere. So this is exactly what we're looking here. Now, first of all, of course, there is another one, a little bit more accurate because of the degenerate point. I made a video about the degenerate points before, why it's bad, and I put the link in the description to this one, so I will not be talking about that too much. What is important here is how we will do an offset for this. Now, remember that I mentioned that in the beginning. Let me just activate the surface offset command, which once again has the same parameters as the curve offset command and have slightly different additional options, but nothing very special, and I will go for this as well. So first of all, let's try to create an offset using the automatic controls, right? So let me just do it. Okay, now I didn't finish my sentence because I said before that in the beginning that you better offset inwards, not outwards. But I didn't specify why. Well, this is a good example why. When you do an offset, remember in Alias and the surface modeling tools, you create outer shells. This tool is designed to create outer shells, basically the A-type surface. There is an A side and there is a B side. A side is outwards to the user, something you can hold, something you can look at, something you can interact with. They're supposed to be very, very, very good. the offset surfaces, as you already understand, can give you a lot of issues, and the quality of the surfaces are worse than the original in 99.999% of situations. So when you perform an offset, always do an offset inwards, not outwards. Otherwise, you basically ruin your work. All your hard work you made, it will be ruined. So instead of doing it like this, change the direction. And when you're modeling something, always keep in mind you're modeling the outer shell. This is your outer dimensions, not the inner dimensions. So always do it inwards. And if something is intercepted for some reason, that means that you either have a poor, technical documentation from the engineering department, or you just, doing some concept designs and never thought about this issue, and that's why you're getting it. So there's, of course, supposed to be it shouldn't be an issue, right? So now, as you're going to see, I have the offset inwards with the automatic, with the offset distance 5, and you're going to see how complex, let me just isolate, how complex it is. Well, yeah, that's quite complex, but let me actually change the curvature, check the curvature now, right? Why not? So we go to the curvature continuity. Oh shit, we're locking tangency. We're locking tangency. We're locking tangency. And once again, we're locking tangency. What's about these ones? Oh, we're locking position. Oh, that's nice. Oh, and position here. And position here. And position here. Well, I will tell you, this is pretty often. Because it's really common, especially on the periodic things. Losing positional tolerance is quite often. And this is a big no-no, so we need to fix that. We can live with the problem with the tangency and curvature if it is an inner shell, which nobody will see. That's okay. But if you are lacking a position within the specific tolerance set, now mine is very tight, I already mentioned that, but for me, this one is like, that's bad. For some situations, may be good enough, but no matter one way or another, we have an issue. So how we fixed it now? What can we do to fix this? Now, first of all, of course, you can let's check keep continuity. Well, let's check and keep continuity, and let's check maybe G2. Oh, shit. Oh, what's going on? Well, you see, when keep continuity works on the surfaces, it's much more complex than its counterpart on the curves, because surfaces are two-dimensional. They have a two-dimensional domains, and curves has only one-dimensional domain. So it can't really solve the continuity properly, especially when you have a degenerate point. And remember, on this sphere, we had a degenerate point with that, which actually, let me actually turn on the zebra stripes. Yeah, you're gonna see this issue. I talked about this issue in the tessellation video. I will put a link in the description as well. I believe this is the one video about the tessellation and degenerate points. So yeah, this is one of the reasons for that. But even though, and there is another example without that, you will see that it will not help us as well that much. So let me just quickly go back and activate it again. All right. So once again, it's outwards. I want it to be inwards. Let me isolate again. So what can we do? Can we do anything? Oops. So the keep continuity is out of option. We can't really do that. Can we do something with the deviation tolerance? Well, it's kind of within our deviation tolerance, and we still see the problems, right? So what that tells us is that this approach, the automatic, is failing on us. Now I can try to click on edge accuracy. And the edge accuracy, in theory, supposed to keep the deviation tolerance not only to the surface, but more specifically to the edges. If you turn that off, it will not take it in consideration. But as you're going to see, it's... maybe actually it works. No, yeah, it works a little bit. So now you're going to see that we have the gap in the different directions. So once again, it's not the case. It's not working. Okay, what other options do we have? Well, if this doesn't work, how about we change the method? So instead of using the CV offset or automatic, we click on the CV offset. Yeah, well, not the cream of the crop. This is still failing for us, and it's just failing even more. And if I will try to use continuity, well, you see what it's giving us. So now this is not an option. Okay. What's about the original? Well, what we have here in the original is that we actually eliminated the problem of opposition. Why was that? Well, that's because we reconstructed these surfaces with the same amount of control vertices as the original surface. So in this regard, it may give you a better result and an easier continuity because the surface is simpler. So now if I will check it, you're going to see that now I don't have an issue with position, finally. But of course, all the other issues are still there. So I have tangency issues all over the place, and they are big. And of course, I have a curvature. So I can go back to explicit, right? This one. And I can try to increase or decrease the amount of elements until I will until it just kind of become better. Maybe remove all the tangency issues. Let me see. Well, probably 5 by 5 give a better results. Let me check. Right. So yeah, to some extent, it's better now. So depends on the model, the specific method which you pick. Can be more beneficial or less beneficial. That's why you have a few. And when it comes to the periodic things like cylinders or spheres, the CV offset will not work. It will never work because the periodic surfaces and its nature really demands a very specific acceleration. The acceleration rate is the same, but the scale is different. So when you offset, you really need to reconstruct them. So that's why we are using automatic approach with explicit, where we can slightly manipulate and change the amount of degrees to help Alias do the job. Now, in this solution, in most cases, that will probably be the end. So you make this stuff. Let me just gonna go in and create the walls. Click here. Now you have the walls. And that's done. So in 90% of the situations in the industrial design, this is good enough, because here probably it will be a cap. There will be like some kind of a overmold, maybe like additional plastic cap with the threads. Here probably will be some holders for some components. So it's not that important. At least we have our position, we have our tangency, more than enough. In a lot of situations in the cheaper products and cheaper materials, position is more than enough. Tangency is not even that important. But of course, situations can be different. So now let's look at this solution. Now this solution, if I'll zoom in, I don't have any degenerate point here, as you're going to see, because now we eliminated the degenerate point. I have additional surfaces here. So in standpoint of a model, this one is more accurate and better. This one is a big no-no. This is a piece of shit. But in return, now we have more surfaces when we need to create a thicken command, or basically create an offset to this. We will have even more issues. Why was that? Because we have more surfaces and we have trimmed surfaces. So basically we have a mask on our surfaces which it masks the part of the domain of the surface. So, and we need to, the surfacing tool, the offset tool, supposed to account these nuances as well. So let's see how it does. So I will go into the surfaces and I will go with automatic. I always start with automatic, actually. It's more of a personal bias, but I believe that in general, it just kind of more often gives me the result I can just leave be. So as you can see, it kind of thinks quite heavily. And the reason for that was because it is just much more complex and I have a really tight tolerance. So as my surface here probably has a different normal direction, let me just change the direction accordingly. And let's wait. All right. So let me isolate. Okay, so you're gonna see it's much more complex now, right? Look, you see, that's heavy. Now let's check. Of course, let's check. So, okay, curvature, curvature, curvature. curvature. Wow, we managed to do that. Let's try this one. Okay. Yeah, okay. And now we have positional deviations here and here and here. So, what you can think about this? Well, what I can say about that? Well, I can say that actually, from what offset is, Alias did a pretty good job. It took my additional surfaces into consideration. It maintained my trimmed edges pretty well, even though that they are very biased. So in this regard, this is quite nice. It even get all the curvature in between, which is even an overkill, but it wasn't able to maintain a gap here. So what are you going to do? Well, as we already discussed with the periodic things, CV offset will not really work very well. So let's go straight into the explicit. And even with the surfaces of 3x3, let me just actually check this. Oops, zoom in. Okay, so even with the 3x3, you're going to see that we eliminated the position here. Now we have position here. Okay, let's try to increase a little bit more. Maybe 5, maybe 5 more. Okay, at this point, I'll probably just stop. Good enough. Now, the offset itself and the actual offset between one object and another object may not be that accurate as it was before. And of course, you need to check it. We have a lot of tools to check this. But that's already on the engineering department. So they can say that this is good enough. That's fine. For the matrix, more than enough. That's okay. We will leave it here. And then you will leave it here. So you're happy that you have curvature almost everywhere, almost for free, because you didn't really do any manual labor, right? And you will keep it here. So as you can see, we have a partial success. In general, this is a success. So you don't really need to do anything else. Right, let's go to the next one. So here we have just a single surface. And if I will perform an offset, my automatic offset, and once again, we need to wait a little bit. Yeah, this is a pretty heavy calculation. So imagine that you have a really complex model. Sometimes it crashes and, that's something you should be prepared. So now we have an offset of our surface. Now, this surface is not periodic. That means that, well, automatic probably will be an overkill here. Why do I need that? Now, it's pretty accurate. So if this will be the inner surface, which I don't want to intervene anymore, I don't want to manually sculpt on that, that's fine. I can just create the walls. Come on. Yeah, we need to wait. Okay, finally. So we have our walls and we can leave it be. So our outer shell is very accurate. Our inner shell, well, is not. But at least we have a pretty good offset, so the distance will be good. Now, what are the other options here? Well, I can go in this time and use a CV offset. Now, why it's beneficial in this regard, instead of using automatic, using a CV offset? Now, from my explanation in the Grasshopper, you already know what the CV offset does. It moves the CVs. And in the situations where the quality, the distance is not that important, and the surface is not periodic, or the construction is not periodic, using CV offset can be very beneficial because, first of all, it's very lightweight. The second, it gives you a surface on which you still can sculpt further on, and the CVs are offsetted from one to another, right? So it can be a pretty good solution when you need to do something here, right? Like, cut something, add additional transition, maybe something else. Not just a Boolean operations on the solids, but in terms of the surfacing. So here, as you're going to see, the CV offset works great. Now, we can, of course, try to use the original, and you're going to see that the result will be quite the same, but it's shifted a bit, because original, you're going to see, I'll click on the CV offset. It's just an offset on the normals of the CVs. Original, if you remember, I already mentioned, this is the part of the automatic process. So even though that it takes the same parameterization, it will not guarantee you that the points will be in the normal direction. It just tries to make the somewhat decent gap between the two, somewhat equal gap between the two. So I would say this is not really very beneficial in this case, right? So this is another example of what it can be. All right, now look at this one. So here we have a surface, and then we have another surface on top of that. Now it is continuous, right? So what kind of approach we're gonna do here? Well, let's try CV offset. As I said, that it's pretty good here. Well, let's try it here. Oh, sorry, not curve, surface, CV offset. And remember, we always need to go inwards, not outwards. If this is the outer shell, of course. So, okay, well, it looks accurate, but if you look closer, oh my God, what the hell is going on? Now, here, we have a gap, a significant one, as you're going to see. That means that when we work with the CV offset and you have a multi-surface construction, when one surface trims another one under the different angles or something like that, chances are that the CV offset will work and give you a clean surfaces are close to zero. This one will not work. Original in this regard will be a little bit better, because even though that it saves the parameterization, it still works with projection of all of this isoparametric lines and then reconstructs. So this is in general more accurate. But if you check it, you're going to see that kind of accurate, but not accurate enough, right? Well, okay, let's go to the explicit then, and we just try to increase the amount of degrees mass ourselves, right? And you increase and increase and increase, and like it's become to be difficult. Now, what was that? Well, that's because these different surfaces has a very different parameterization. They are not following the same direction, not even close. They have different amount of degrees between each other, and they are not periodic. So in this regard, the better solution will be to use automatic instead. So let me just select this. Wait, of course. Yeah, that's painful, I know. Okay. So it kind of makes it in the other direction, but whatever, doesn't matter. So, well, we still have our gaps. It didn't really pan out for us. So we can say, well, I would like to keep continuity. How about that? This is not a circular shape, so maybe that will work. Let's give it a try. Okay, so it tries. Didn't really pan out very well, but it tried. Okay, the last thing which we can try is the option called edge accuracy. I already said that the edge accuracy will take the same deviation, but for the edges. So for all of these edges, and from the true edges of this patch. Not the one that was stripped, but the one which is sitting on top of that. Kind of our last resort. Well, let's try. And as you're going to see, it didn't really help us much. So basically nothing really happened. Nothing good happened at all. So we have our deviation. Actually, no, it's actually helped us. Yeah, no, it's actually helped us. Not necessarily very much, but at least we removed the positional issue. So well, that's it. And once again, that's because it takes these edges and use the same edge accuracy as for this surface, and basically it's pretty tight. So don't remember about this tool. This option can be helpful sometimes, especially when your surfaces are trimmed. Okay, but this is not the full story. What if I would like to create a cleaner surface and I would like to maintain the because I want to sculpt it. Maybe I want to change this. So I can go back to the surface offset, and I'll go to original. Sorry, it's down like this. Let me remove the create wall. Go back here and look at the original approach. Once again, it works with the automatic and we have these issues here, right? But even though that we already sacrificed to some extent our equidistant between the two, if we already did it in return, we get a pretty clean surfaces. So what that means, that's right, I can retrim this, this surface, just delete this, these curves, and guess what? I can just reproject. And this approach can be quite useful and pretty often used when you create the B side of the model, and you kind of ready to again, just rebuild this too. You're kind of prepared for the fact that there is some discrepancy in the offset, but you still need to sculpt on it. And of course, in these regards, the CV offset and original with automatic will be quite helpful because it still gives you an ability to do that, right? So it's definitely better than, million gazillion spans and, the solution with some deviation, which you definitely can't fix because there's just too many spans, right? So this one definitely will work better. But as you're going to see, every single one of them has flaw. You sacrifice one over another, and there is no situation where everything is perfect. That's the nature of the offset. Okay, let's go to this one. So this one, as you're going to see, it was a surface, and it cut in form of the a circular shape. It has a circular cut. Now, if I will, and this is just an example for a specific option, which I didn't really specify, but I want. So this option called shrink to trim. Right here, it's activated. So let me just deactivate. I'll go to the CV offset, and I will click on the surface and activate its domain of control vertices. So as you're going to see, I have a CV offset method activated. I move to the geometry. Once again, don't remember, if this is the outer shell, always goes outwards, inwards. So as you're going to see, the surface itself is still intact. So it has the same domain and the same parameters, but just trimmed, offsetted and trimmed. But there can be situations when this is not desirable. When you want the surface which was trimmed after an offset will be contained within the bounding box of an object. The bounding box is basically the cube which holds the trimmed area. And this box reparameterized the surface. So if I will click shrink to trim, and let's just kind of try it again. Oops. Probably let's try automatic here. Yeah, here it is. It's not always works with the CV offset. Sometimes it does, sometimes it doesn't, but the automatic always does. And you're going to see what happened. Without the shrink to trim, it's big. With shrink to trim, well, now it's small. So it reparameterized it to the edges, and it sometimes becomes to be very useful, especially if there is a lot of objects and it's difficult to pick the proper one, or you need to do some UVs or some parametric modeling, doing patterns and stuff like that. The fact that the surface is contained within the bounding box can be pretty useful. Now, this is not for everyone. I would say in 80% of the time you don't even bother what's happening with them, but I would say that in the situations where you need UVs or you need, the proper visibility, or if you want to keep sculpting, but you make a trimmed object, but this is not like this one, which is contained already, right? This one, it's already contained. I offset already contained one. This one was not contained, but I would like to work specifically with this piece, right? It will be very helpful for me if I ask it to shrink, because now I have the proper rectangular shape for that. So as you can see, it's quite a useful component. Now, the both sides, I will believe, self-explanatory. Create walls, you definitely understand what it is. Edge accuracy, I'll explain. Keep continuity. Well, you already see that it's not always work the way you want, even on a simple examples, because all of these ones are quite simple, right? You will have much more complex solutions than that. So, as you're gonna see, even though that the offset command in Alias can give you a lot of variety and a lot of options. Doing offsets for the surfaces, especially if it is a collection of surfaces, is always tricky, and it always flawed, or like it's 99% flawed in one way or another. That's why one of the golden rules is always offset inwards. Even if there's something bad will happen with this, you wasn't able to maintain curvature, but because of you maintaining distance, at least it will be something which users will not be able to catch. They will not see it, right? So now let's talk a little bit about the place of Alias in terms of the thickening and making thickness to the models in the scope of the whole industry. So as Alias is a surfacing tool, and it can't understand the concept of solids, as I said in the beginning of this video, in the introduction, that means that it's offsetted objects. Now let me just kind of create this one, and I will just use the let me go and say create wall. So yeah, here it is. So now when you have object like this, it's actually hollow inside. Basically, like, you can think about that as a polygons, right? You create a polygonal model, you look inside of it, it's empty. It's hollow inside. This is the same. This object is hollow inside. It doesn't have any material within it. It is just a depiction. So in the real world, in the real battle scenarios, what will happen is that you take the thickness of the material into consideration, you do the proper flanges if they needed to be, but you're not giving thickness. So you're not doing any thickness here, you're not doing thickness here, you don't bother about that at all. You leave it as a surfaces, just as surfaces. And then you toss all of this data, all just separate surfaces, to the engineering department, and they use the power of solid body modeling tools, like, I don't know, like SolidWorks, and they will do the thickness using their own instruments, like a shell or thicken commands. And there is a lot of chances that it will work just fine. These tools are pretty robust as well, and their thickening commands, even though that, as I said, it's based on the offset, they are pretty robust on its own. They can do a lot of good stuff. And there is a lot of chances that you will not hear of the engineering department again. They will do, and everything just fine. Everything will work. But if the project is complex, if the surfaces is complex, there is a lot of surfaces, they join together by the different angles with different domains, a lot of trims. The chances that SolidWorks or, I don't know, CATIA, whatever, can really make the proper thickening option for your model are quite slim. So they will try to do it, and in most cases they will fail. And when solid body modeling tool fails, it will return, well, nothing. It will not give you a thickness with failure. No, it just didn't really do a thickness. So you may imagine what will happen next. So the engineering department, the guys from there, they knock your door, knock, knock, knock. And I will tell you that, hey, guess what? It's we can't do it. It's too complex. So now it's become to be your headache. What do you think will happen next? Well, that's right. You will go in and then you manually do what I actually showed you here, using the different combinations of the offset command, manual adjustments, manual reprojections, and a lot of other things to achieve the desired goal. Is it to be a position with proper distance, or the distance is not that important, but it wanted to be at least tangent or something like that? You keep it in consideration and you do it manually. So that becomes to be a manual labor. And when you're done with this and you build this shell, this one, the next stage is to convert this collection of surfaces into something that other systems, especially solid body modeling systems, can understand as a container for a material. Now, in Alias, these tool, which kind of creates a collection of surfaces, the constrained collection of surfaces, instead of just randomly placed surfaces or just like this, just not really tied together surfaces, it's called stitch. So we have a specific tool here called Stitch. Let me just actually show it to you. Stitch. So this one. Now you go to the shell Stitch. Let me just activate that. And stitch this one. And this become to be a stitched version of the model. Now in Alias, it's called stitched version of the model. In all other CAD systems, it's called a BREP, or boundary representation, or even better say closed BREP, which means closed boundary representation. Closed means it is watertight within the desired tolerances. It has internal volume, it's closed, it's watertight. And then you toss these objects to the engineers, and then they will use this to guide their instruments and tools to create material within. And guess what? It's not always works as well. There can be situations when everything is done right, and you have your the stitched model, or BREP, closed BREP, you toss it in, and it still no stitches. And then basically the cycles continues. Rinse and repeat, rinse and repeat. The more complex your model is, the more painful it is to do for us, for designers, and as well as for engineers. But this is just the tip of the iceberg, because eventually when we go into mass production, I already mentioned it before, you need to create a matrix for that. And the matrix works based on the offsets. And they're supposed to be extremely accurate. That means that it is just a whole new level of complexity and pain. Luckily, these days, manufacturers, almost all the manufacturers take it under their control and do it themselves. But sometimes there can be situations where, they go back into the design bureau and said, no, the matrix is just on you as well. And that means that you will spend more time doing offsets and matrix and die than actually building the model itself. This is the reality, the reality of the industry. Now, before I get to the conclusion, I already mentioned the BREPs as a boundary representations. And if you ever wondered, because there is a lot of different terms thrown around in the internet, especially when you try to figure out what is what. So let me quickly clarify. The stitched model is true only to Alias necessarily. In general, as I said, it's called BREP. But the BREPs can be two types, the open BREP or a closed BREP. For example, let me just delete this stuff, right, from here, and I will stitch it again, right? Okay, now as you can see, this bright yellow line. Well, that means that this BREP or stitched model, it's stitched only here, and you have an empty side here, so it doesn't have any internal volume. This means that this is a closed BREP, and this is an open BREP. And the open BREPs in the industry has a different name. So you can call them open BREP, that will be true as well. But in general, they also has a second name. This construction called polysurface. So the polysurface and open BREP is the same thing. And the closed BREP is the closed BREP. So there is this difference. Now, in terms of the surfaces themselves and how they operate, as you're going to see, I can't really modify. I can't even activate any CVs or anything like that with this model. It's still a surfaces. They are still separate. You can easily kind of convert it back, actually. So all of this information saved, but Alias strips away the options to change that, the same as any other CAD systems, because all of them now, with this current construction, has a very specific flag, which treat them as a BREP. And surface modeling tools, when it comes to the BREPs, they kind of strip all the controls out of you. So if you want to proceed, you need to unstitch. We have this option called unstitch, and I can unstitch it now, and you're going to see I have all this stuff back. But the true solid body modeling tools, they actually can work with these stitched versions, and they can't work with solids. The moment you convert it to the solid, you can do fillets, you can do Boolean operations, stuff like that. Now, we can do Boolean operations in Alias too, but the options are quite limited. Well, anyway, so as a conclusion, guys, the right way to give thickness in Alias is to use an offset command. A specific algorithm within can vary based on your situation, as I showed before, but all of them can easily fail one way or another, forcing you to manual labor. So it's always a pain. It's always like, it always will fail one way or another, and it will force you to intervene, in most cases manually. And as for the golden rule, there is only one. Always offset inward, not outward, as offset surface always will be worse than original. An outer shell is more important in terms of its quality than the inner one. And that's it. Thank you very much for watching, and I will see you in the next one.